So let me tell you a little bit about this section, okay? One thing we're doing now is we're going to look at two variables, okay? Like age, the age of the person and the income of the person, right? And we're gonna try to get some insight as to how these two variables are related, right? As age goes up, what happens to income, right? Does it go up, down? Well, it usually goes up with age, right? At least on average, until you retire, then it really drops back down, right? So that's the point of this section, okay? To look at two variables and to compute and to use measures that will tell us something about how the variables are related. Very useful topic for, when you're running a business and you want to predict things. What's going to happen to sales? But wait, what are the things that drive sales? And how it's related to sales, right? So you need to know about variable relationships, right? So it's called measures of association, all right? We're going to look at two of them. So let me tell you a little bit about the formulas, because it gets really a little overwhelming, right? We've seen so many green boxes today, and there are more to come, okay? And it's like green boxes times 2, because we get one for samples and one for populations, right? It's like everything repeated, okay? So let me tell you about these 4 formulas we're going to see here, okay? It's really 2 formulas, right? Really 2 concepts, covariance and correlation coefficient, but times 2 because we got to look at the formula for the sample and then the formula for the population, right? Now, as far as the correlation coefficient, the formulas are different just because of notation, okay? The only difference comes from notation. So as far as computation, same thing, okay? And when it comes to covariances, the formulas are different because of notation, but also because of computation, okay? There's a slight difference between the 2 formulas in terms of how they're computed. Just like the variance formulas, right? How they were slightly different because of the n minus 1 and the big N, right? Very similar, okay? So just so you know, this topic is not on chapter 3, it's on chapter 14. But on your homework, it's all already there, right? So you do have a homework question on this one and a quiz question on this one. All right, I should say that again. This topic here is in chapter 14 in your book. So if you don't find it in chapter 3, then you got to go to chapter 14 and find it. Okay? It doesn't make it more difficult because it's in chapter 14. In every book that I've seen, actually in the new edition of the book, they moved to chapter 3. So if you have the new edition, which I doubt you would, it's just too expensive. Really, why would you buy the new one? You will find it in chapter 3. Okay? Covariance. The covariance, just think of the name, covariance, right? It's going to be very similar to the variance. Okay? It's going to be very similar to the variance formula. So covariance, the co, you can think of it coming from the word co-movement, right? The covariance measures the relationship between two variables, but it measures the linear relationship, okay? And that's a key word there, okay? Linear relationship. So when I say co-movement, I'm saying when variable x goes up, what is variable y doing? Okay? Is variable y going up? In value, I mean, right? When variable x goes up in value, what is variable y doing? Is it going up? If it is, then they're positively related. If it is going down instead, they're negatively related. So basically, if 2 variables move in the same direction, we say that those variables have a positive relationship. If 2 variables move in opposite directions, we say that those variables have a negative relationship. If 2 variables don't have any relationship, then we say that they have no relationship, right? So the covariance will be 0. Okay, so let's look at how that translates into the covariance. 2 variables that have a positive relationship, that means that they move together, right? Are going to have a covariance that is going to be greater than 0, positive covariance. 2 variables that move in opposite directions are going to have a negative value for the covariance. And 2 variables that have no relationship are going to have a 0 covariance. How is that? Good. So you take two variables, x and y. Now we're looking at two variables, not just x, but x and y, right? X and y, two variables. You compute the covariance. The sign of the covariance is really most of what we care about. The sign of the covariance. But we also care about the size of the number. But the sign of the covariance, whether it's positive, negative, is telling us about the relationship, whether it's positive or negative. Okay? So if you think of age and income, if you look at those two variables, should they have a positive or negative covariance? Positive. They tend to move together, right? As you get older, on average, I'm not saying that everybody does that, right? You may decide to stop working at the age of 30, right? Or whatever, okay? But as you get older, you tend to earn more money. For age is a variable, income is another variable. They move together, okay? It's hard to say as you get younger, you make less money because nobody gets younger, right? But in theory, as a variable goes down in value too, right? The other variable goes down in value as well. If they go together in the same direction, they're positively related, okay? If they go in opposite directions, they're negatively related. All right. So how does the formula work? Do you see a difference? I like actually having the formula side by side. It's much easier, right? You can just see the difference, okay? Difference, of course there's a difference. There's a difference in the notation. Instead of x bar, we have mu, right? Instead of small n for the sample, we have big N. Instead of S sigma. Now be careful, right? This is not just S as in standard deviation. The subscript here is very important, right? What is the subscript? XY. So there's a difference between this. They are very different things. What do you think S of X is? Get somebody else. Anybody with, what do you think S of X is? This one here. This one would be the standard deviation of the variable X. That's something that we've seen already before the break, right? The standard deviation of variable X. This is going to be the covariance of X and Y. Even though they look alike, they're very different things, right? What would this be? That's a Y, by the way. The standard deviation of variable Y. All right? So I know there are very small differences in the notation, but they should be making a big difference in how we interpret them. Okay? These are standard deviations. I mean, I could come up with anything. Standard deviation of H. Say H. The standard deviation of the variable H, right? I call it X, I can call it Y, I call it whatever I want, right? This is the covariance between variable X and variable Y, whatever they are. Okay, so now we need data on what? We need data on two variables, right? We need to know what is the data for X, we need to know the data for Y. So for each person in our sample, we need to know how old they are, how much they make. 2 data points per person. Before it was just one, X. Now we need X and Y, so that we can look at how these two variables are related. All right? So that's one thing. Be careful with, the subscript tells you something. The other thing is, you see how we have Y bar here? That's going to be what? The average of the other variable, the new one. Okay? And here we call it mu Y, right? Mu Y. Mu X, mu Y. Okay? Everything is the same. So notice the big difference between the two formulas, to me, is this down here, right? N minus 1, just like as in the variance. Here, N. Okay? All right, so let's see how we compute it. We don't need an example for this, huh? Yeah, and I have one here, so let's do it together. Okay? This is one of the problems that I asked you to do on your own. We'll do it together, okay? So the covariance first, because that's all we talked about, right? And then the correlation coefficient. What I'm going to do is I'm going to use the sample formula, and I'm going to write it out here so you remember it. XY equals sum xi minus x bar yi minus y bar I equals I divided by n minus 1. I don't have an example, do I? Hold on one second. Okay, so that's the formula that we had, the one for the sample data, right? You see how you know how the population one changes, the notation changes, and all that. So let's apply this formula. Okay, what I want to do is I want to do it on a table format. Much easier, much better. It looks like it's more work, but it's much more organized. So let's start with this. What are the first three things we need to know before we start computing the covariance? The two averages and what else? One thing that we know, so it's given. The sample size, right? Just like before, okay? So what is n? What's n? Diana? This n. What is it?
Is it all 5 of them?
Maybe. Is it?
Yeah.
Yes, it's 5. You got it. It's 5. You have 5 observations, right? You've basically, this is person 1, person 2, right? You've asked them 2 questions instead of 1. So you know 2 things about them, like their age and their income, right? Okay? So n equals 5. There's 5 observations. What about x bar? That's going to take some time. This one is going to take some time, right? So x bar is going to be what? 3 plus 5 is 8 plus 12, 20, 25 divided by 5, 5. That's x bar. Y bar, 1.3, 2.4, 3.9, 3.4 divided by 5. 0.68. Thank you. Now we have everything we need to start working on the covariance. Okay? So the covariance is good. Now it would be nicer if we had an example in which, let's do this, okay? If we have time at the end, we'll go back to this and do a problem with some sort of story behind it, like some context, okay? But remember, this is just one variable, and this is a different variable, right? And you wanna see how are the variables related? Do they move together or not? Now, in this case, our data set is so small, right? We only have how many observations? We said 5. So you can sort of glance through at the data, and you get an idea, right? Do you think the covariance is going to be positive or negative in this data set? Just by looking at the data. Don't compute anything yet. Sarah? Negative. Is that right? Brittany, what do you think? So the covariance tells you what? It's a measure that tells you how 2 variables are related in the sense of how do they co-move, right? Do they move together or not? Okay? So by looking at the data, so you go from the left to the right, you can, such a small data set that you can tell, right? If you had 100,000 observations, you could never tell. But in the 5 observation data set, you can. So look, this goes up, this goes down, right? This goes up again, this keeps going down. This goes down, this goes up, this goes down, this goes up. And I know this is contradicting, right, at the end. But on average, you see the pattern, right? And what we care about is not what happens as we move from person to person, right? It may not be perfect, okay? May not be perfect, but there may be a pattern, right? And the pattern here is that they tend to move in opposite directions. So when you compute the covariance, you should expect it to be negative. So let's work on it, okay? All right. Let's do our Excel table. Okay, I'm not going to open up Excel because some people get scared when I use Excel. So I will do the same thing on the board. It's going to look like Excel, but it won't be Excel. All right. Xi says what? 3, 5, 12, 3, and 2. Yi, 0.9, 0.4, negative 0.5, 1.1, 1.5. Now what? Now it's good to write the averages, right? X bar, Y bar. 5, 5, 5, 5. I don't know if you guys can see. Can you guys see that? Yeah? What's her name? It's too late. Brittany, can you see that?
Yeah.
And your name was? Gabby. Good. She tried to tell me, but I couldn't tell. Okay, so 5. Y bar is going to be 0.68. So that's sort of the setup, right? Now we actually have to apply the formula. Now look at the formula, okay? You're going to take, again, you start with the first observation, right? The first row. Take the first value of x minus x bar. Whatever you get is called x in deviation form, right? Multiply that difference times y in deviation form. Okay, so let me create a new, I'm going to run out of space, so I'm going to have like a big column here, which is going to be xi minus x bar times, right? yi minus y bar. So this is this whole thing times this whole thing, right? You have two things, you're multiplying the two. That's all, okay? So let's see what it would look like. I'm going to write it out. 3 minus 5, what would that be? Negative 2. And here we have 0.9 minus 0.8, 6.8, right? So we basically have negative 2. I'm going to just show you everything for 1, then we can do it for the rest, okay? This is basically negative 2 times 0.22, yeah? So what are you going to get from this? Negative 0.44. Notice one thing. The number came out, what sign? Negative. Why? Because, this is why. Because in the first observation, the value of x was below the mean. Correct? That's why it was negative. But in the same observation, the value of y was above the mean. So the y difference is positive, the x difference is negative. When you multiply the difference, you're going to get a negative product, right? That's what happens most of the time. Most of the time, when x is below the mean, y is above the mean. Or when x is above the mean, its own mean, y is below its mean. That's why the products are going to end up being mostly negative. Okay? And that's going to take you towards a negative covariance, because that's basically saying when you're high, I'm low, right? When I'm low, you're high. Okay? All right. Now, I did it for 1. In Excel, I would just click and drag down, right? I cannot go through all of them. It's too much. Okay? But as you go through all of them, you will notice that most of the numbers that you get in this column are going to be negative. You will notice that. In this case, right? Because the variables are negatively related. So what's the next step? Look at the formula. What's next then? Once we get this product for every single one of the observations, what do you do next? Brittany? Before that. The question I asked is, once you get this number, right? In this case, it was 0.44 negative. But once you get it for every single observation, now you have a list of them. What do you do next? Add them up, right? That's what this means. Add them all up. Now you're going to get a sum, a single number, right? And then you divide it by 4 in this case, correct? Now, of course, this number is always going to be positive. Do you agree? Because the sample size cannot be negative. That makes no sense. Or 0, right? If you have 0 data, you have nothing to do, right? So the sample size is always going to be positive. So the number down here is always going to be positive. What's going to make the covariance negative is what you get up here, right? Okay, and we sort of figure out that we're going to get a negative sum on the top, right? If you keep doing it, you should do it. You should finish this exercise. You're going to get a negative sum. Divided by a positive number, which is the sample size minus 1, you get a negative covariance. So let's see what the covariance should be. Oh, God. Down? Yeah. Negative 3. I hope my slide is right. I got 2 typos already today. Alex?
No, so there's no like we do with the standard deviation. There's the variance, like there's no squaring involved, right?
No. I can ask you a question though. Maybe we can figure this out. What if I were to do this? Gabby, why don't you help me out with this one? Since I know your name now. What if I were to take y, right? I'm going to take y, I'm going to erase it. And I'm going to, instead of y, rewrite x. I know it sounds weird, right? But I would just erase y. Let me do it. Do this, right? And I'm going to write xi again. So 3, 5, 12, 3, and 2 again. and I want to find what is the covariance between x and x. Okay? What would I get? No? If I try to find the covariance between a variable with itself, huh? Syntax error? No. 1 is not the answer either. Think of what would happen. Of course, I would need to take this out, right? Because I'm not using y anymore, and use x bar again, which is 5 and 5, right? If I do that, what would happen? Well, look at the formula. What would I be doing? I'll be replacing y for x. That's what I just did, right? So if I do that, it'll be xi and x bar, which is basically what?
Square.
Just this and get rid of this. What is that? What do we call that? The variance. That's the variance formula, right? So the variance is simply the covariance of a variable with itself, okay? So if I take the covariance of x and x, I might as well call it the variance, because that's what I'll be doing, okay? So the variance is just that, is the covariance of a variable with itself. And I know that you had a tendency to say 1, right? Because if you think, and that's a good tendency to have, okay? If you think about it, how does one variable covary with itself? It's the same thing. You're basically, this thing goes up by 2, this thing goes up by 2, because it's the same thing, right? So yes, in a way they're perfectly related. Positively, of course, they move together. Positively, perfectly related. Okay? But what I was trying to get at is the formula construction, right? It's really, the covariance is not very different from the variance formulas. They are the same sort of formula. All right. So -3, what does that mean? A lot of most of the information that we really get out of the covariance is the sign, the direction. How are they related, positively or negatively? Negatively, because of the sign. The number tells you very little, unless you're comparing two different sets of variables. Okay? So just to simplify it, when you compute the covariance between two variables, really most of the information comes from the sign, right? Is the covariance positive or negative? Well, if it's positive, the variables on average move together. If it's negative, the variables on average move in opposite directions, right? Okay, remember how we went from variance to standard deviation? It was one additional computation, right? Now we're gonna go from covariance to the correlation coefficient. Now, correlation is a term and a word that we use. Maybe not on a daily basis, maybe not on a weekly basis, but on a monthly basis, right? You probably say correlation once a month. Okay, maybe. Don't you? Do you guys ever use the word correlation for anything? Sometimes, right? Even if it has nothing to do with quantitative academic knowledge, okay? You may use it, okay? So we do have an idea of what correlation is. Well, correlation is not much different from covariance, okay? Correlation tells you about how two variables are related, okay? To be more technical, it tells you about the linear relationship between two variables, okay? Well, that's exactly what the covariance told us, right? Why do we care about another measure that does nothing different? Well, it does something very different. In the case of the covariance, when you get something like -3, what do you conclude? You conclude that x and y have a negative relationship, right? They move in opposite directions, okay? But how strong is the relationship? We don't know. We just, -3, is that strong or weak? We don't really know, okay? So to know about not just how the direction of the relationship, positive or negative, but also the strength, we need to compute the correlation coefficient. So the correlation coefficient tells us a little bit more of information, okay? It's gonna tell us about direction, but also strength. So we can say things such as, these two variables are strong positive correlated, or weak positive correlated. That could be the case, right? Or strong negative correlated, or weak negative correlated. So besides direction, we also get strength information. Okay? Correlation coefficients. Oh, where did it go? Oh, it was before that. So these are the formulas, more green boxes. Look at the formula. Now you may be thinking, well, there's a lot of work to do to get to the correlation coefficient. Look at the sample notation. All right, the sample notation says what? The formula consists of 3 numbers, right? 3 numbers. What's the top number here in the numerator? What do we call that? Covariance between x and y. What do we call the numbers down here? There are 2 numbers, right?
Standard deviation of x.
Good. Good. So look at all the work you gotta do, right? To compute the correlation coefficient between 2 variables, you need to compute first the standard deviation of one of the variables, then the standard deviation of the other variables, and then the covariance of the 2 variables. That's 3 computations before you can actually compute the correlation coefficient. Of course, if you know Excel, you just type the equal sign and then CORREL, and then put the data in there. Okay? It's much easier, right? But if you do it by hand, it takes a lot of time, right? For a data set of, let's say, 10 observations, it will probably take you 10 minutes or more, okay, to get to this. All right? But once you have these 3 numbers, you have the covariance, the standard deviation of x, the standard deviation of y. I don't know how used you are to quantitative courses, but if you ever see one thing and then right next to it another thing, right, they're multiplying. If there's a space between the 2, that means they're multiplying. Okay? Usually when there's a space between 2 things, 2 distinct things, they're usually multiplying. Okay? So there's a number here, the covariance divided by the product of the standard deviations of each individual. Now for the and the correlation coefficients, the label is R, right? R, X, Y. If you're looking at the population correlation coefficient, just change the labels, nothing different, right? The formula is identical except for the notation changes, right? Instead of, we have Greek letters here, right? So we have sigma xy, sigma x, sigma y, and here we have rho, the Greek letter rho, xy, okay? Now, let's talk about this, the contribution of the correlation coefficient. Why is it better? Because of strength, we said, right? So it's when you compute the correlation coefficient, you're basically forcing your measure, your numerical measure, to be between a given range. So this formula here forces your outcome, your numerical value, to be between -1 and 1. So when you compute the correlation coefficient, your correlation coefficient must be a number between -1 and 1, including the endpoints. It could be -1, and it could be +1 too, right? So it could be, if you ever are working on a problem, and you finish the problem, like after 45 minutes, you're exhausted. You got the correlation coefficient, right? And it comes out to be 3.5, you got it wrong, okay? It cannot be outside the -1, +1 range. By construction, this formula forces the answer to be in that range. So that's a way of you checking your own answer, right? Okay, troubleshooting, right? All right, how is that? So let's see how we interpret numbers then, okay? What needs to happen for the correlation coefficient to be 0? Let me start somewhere else, actually. These are good questions. The standard deviation of x, can that be negative? Can the standard deviation of a variable be ever negative? By the way I'm asking you the question, you sort of know the answer, right? I don't know, maybe. Can the standard deviation of a variable be ever negative? The answer is no. Remember how we compute the variance? We square numbers, right? When you square numbers, you get rid of all the negative signs. Right? So when you go from the variance to the standard deviation, your standard deviation cannot be negative. Okay? So the standard deviation of x has to be either 0, in which case there's no variation, or most likely it's going to be positive. Same with y. So if these 2 numbers are positive, when you multiply the 2, what do you get? A positive number. Right? So how can then the correlation coefficient be ever negative? Because the covariance could be negative. So what I'm trying to say is that the sign of the correlation coefficient comes from the covariance itself. Right? So if you know the sign of a covariance, then you know the sign of a correlation coefficient. It's the same. So why then? Why do we have the correlation coefficient? Because now we can say something about strength. Okay? How? Let me go straight to the point. The closest the correlation coefficient value is to either -1 or +1, to either end, the stronger the relationship is. Does that make sense? So something like 0.95, is that close to 1? Yes. So that means that those two variables are strongly related, right? Very strong relationship. What about -0.95? Is there a strong relationship there too? Yes. Yes. You need to be far from 0 to have a strong relationship. So one place in which people get confused is when, they're like, well, -99, that's weak. Why? Because it's negative? No. Okay, one thing is the direction, positive or negative, and different thing is the strength, weak or strong. Okay, so you can have two variables that have a very strong negative relationship, like -0.9. Okay, so as you move away from 0, so if we have like well, I should be here, -1, +1, 0. Right? I guess we shouldn't have this, right? Because these are not possible outcomes. Okay, that's our correlation coefficient set of possible values, right? As you move away from 0, in either direction, this means that your relationship is stronger. Okay? As you move closer to 0, then your relationship is weaker. So here, you are in a strong positive area, right? Here, you are in a strong negative area. Here, you are in a weak area, right? Weak area, where there is weak negative or weak positive. All right? What about here? I don't know. It's all relative, right? It's all relative, okay? So when you get a correlation coefficient of 0.9, then you know that's strong, right? Why? Because it's close to 1. What about 0.5? Oh, that's hard to interpret, okay? It's stronger than a different set of data of variables that have a 0.1, yes. But, all right, so do you see where we get more information now, right? Since we have boundaries, we know when the relationship is strong or weak, okay? So that's the big contribution of the correlation coefficient. Now, one thing I should be warning you about is this thing here. Correlation does not imply causation. Do you guys remember when we talked about? Did we? I'm doubting myself. I think we did. We talked about, yeah, we did. Independent variables and dependent variables, right? Last week. So in economics, for example, right? If I tell you price and quantity, which one will be independent and which one will be dependent? Two variables, price and quantity. Which one will you label as independent? Independent? Would you? Price? So which one will you, okay, let me ask the opposite question. Which one would you label as dependent? Price or quantity? Quantity, right? I mean, everything moves in circles in economics, right? Everything affects everything in a way. But, if you had to pick one answer, it would be price would be the independent variable. As we change price, but I guess I should be more careful with the question, right? Let's change the question. Price and quantity demanded. That makes it a little more clear, right? Because you have quantity supplied too, right? Price and quantity demanded. That's a better question, right? As prices change, quantity demanded reacts, correct? So price will be the independent variable, quantity demanded will be dependent. So in that case, we're talking about causation, right? Price causes quantity demanded to change. Okay? Did we need any numbers to come with a conclusion? Did we have to go through any data work? No. It comes from just understanding things, how things work, right? Theory. So causation has to do with which one is independent, which one is dependent. Okay? Correlation does not tell you anything about causation. Just because two variables move together, it doesn't mean that one causes the other one to change. That's the point I'm trying to make. Okay? Very important point. All right? Just because two variables move together, so they're positively correlated, does not mean that the increase in one variable causes the other one to increase. All right? That's not necessarily the case. Okay? All right. So now we can talk about, wow, that would be a lot of work. That's a lot of work, right? Because the only thing we have is what? Covariance, right? So, well, at least we know the process. So let me explain the process at least, right? This is what you will need to do. You will need to take this formula, not this one, sorry. This formula and compute the covariance, which we just did. Well, we didn't finish it, but we got close to it, right? And it would be equal to what? -3. Okay? Then you will need to compute x, the standard deviation of x, right? What formula do you need for that? Square root of some xi minus x bar squared divided by n minus 1.
But to do that, you have to do the whole thing over.
The whole thing over, yeah, because it's not the same as this. See, in this case, you take the x difference and then you square it. In this case, you take the x difference and then you multiply it times the y difference. So these are three different computations, okay? And then you will need to take sy, right? So compute this one, then this one, then this one. Now, these two we did before the break, right? So you should be able to go through the process, okay? But once you have all three, then you need to compute the correlation coefficient, which is going to be -3 divided by Sx times Sy. Now, I don't have these two numbers, and it would be way too much time for me to compute it, okay? But you should get an answer. Let's see the answer. The answer is the correlation coefficient. Well, if you cannot answer these two. Do you see why these two are wrong? Why is that?
Because there's a -3.
I'm sorry?
There's a -3.
Yeah, but forget about the -3. Why would these two be wrong? Regardless of, without you even knowing the covariance. Yeah. Because they're opposite signs. That's not possible, right? It's the same data set. They have to have the same sign, the covariance, and the correlation coefficient, right? Because the covariance is what gives the correlation coefficient its sign. So this cannot be true, this cannot be true. Okay, so you get 50% already out. Now it's a 50-50, right? Could be this one or this one. Now look at, actually, we need no computations for this one, now that I think about it, right? If you think about it, I'm asking you for the covariance first, and then the correlation coefficient. So can this one be the answer? Why not? Yeah, because the correlation coefficient cannot be outside the -1, 1 range. So you can cancel this one out. You can eliminate this one. Now you know the answer without doing any work. Okay? Right? So the correlation coefficient is -0.96. What can we say about these variables? How are they related? Katie?
I guess strong negative.
Relationship.
Related.
Yeah, that's right. So x and y have a strong negative relationship. They're definitely strong, right? 0.96 is very close to 1. So to -1. Okay? There are two more terms that I want you to know about before we move on to our biggest topic of all semester, term, 5 weeks. And that's perfect correlation. When two variables have a perfect correlation, that means, well, in terms of the numerical value, that means that the correlation coefficient is either +1 or -1, exactly. So it's as strong as it gets, right? So if the correlation coefficient is +1, then you have a perfect positive relationship. That doesn't exist, right? Perfect positive relationships. If the correlation coefficient is -1, then you have a perfect negative relationship. Okay? So you add the word perfect there because it's right at the edge of the range, at the end of either side. Okay, z-scores. Z-score. The z-score is a term, a concept that I'm gonna use when I'm gonna use starting chapters. So of course today, because we're talking about it for the first time. What time is it? Whoa, it's late. I'm gonna have to keep you here the entire time. The z-score is a term that I'm gonna talk about today, but also in chapter 6, 7, 8, 9, and so by the time we get to like chapter 7 and 8, you really know what the z-score is. It will become a tool, not something you need to learn. It will be something that you use, that you know very well. Okay, but see, if I say it, if you read this, right, you may be thinking, what is that, right? How can that make any sense? But the z-score is basically the number of standard deviations that an observation is away from its mean. Does that make sense? How many standard deviations a given observation, a given data value, is away from its mean? That's basically what the z-score is. That's what it means. The z-score measures distance between what? Between a given observation, you pick the observation, and the mean, but the distance is measured in what units? Not in dollars, not in yen, not in feet. Is measured in standard deviations. Okay? So, to simplify it, let me build a data set. Of course, I'm not going to build the entire thing, but let me just come up with some numbers, okay? 8, 12, 0, 6, 10, and more, okay? So this is your data set, right? I don't really care about the entire data set because I'm making it up anyway, right? Out of this data set, let's say that x bar equals 7, all right? You can compute the average, right? I mean, this keeps going, right? There's, I don't know how many observations. This is a data set, right? And let's say that S of x, which is the standard deviation, right, is equal to 2. Okay? Can we compute this? At some point, we have to be really good at it, okay? So you compute the mean, then you compute the standard deviation, and these are your numbers. Then I go back and I say, okay, pick the first number. Which one is it? This one, right? Take that one. That's our first observation in the data set, right? And tell me, how far is that number from the mean? Now you may say what? 1. That's true. It's 1 away. So let's say let's give some context to this. Hourly wages. Okay? So dollars. Dollars, right? Hourly wages in dollars, okay? How far is the first observation from the average wage? And the answer is $1. Do you agree? $1 greater than the average. Fine. That's true, that's correct. But if I were to ask you, how far is the first observation from the mean, but don't measure the distance in dollars, measure the distance in standard deviations, what would your answer be? Alex? Half. Do you see why? Gabby? No? Well, how big is one standard deviation? How big is the standard deviation? 2. How far is 8 from 7? 1.
Oh, okay.
That's half of the standard deviation. So how far is this observation from the mean? It's $1 away. That's one way of saying it, right? But in that case, we're measuring in what? In dollars. But what if I don't want to measure in dollars? I want to measure in standard deviations. You may be saying, well, you're crazy. Why would you ever do that, right? There's a reason for doing that, okay? That we won't see it yet. If I were to ask you, how far is 8 from 7? with the distance being measured in the number of standard deviations. Well, you know that one standard deviation is 2, right? So 8 is half a standard deviation away from 7. So said differently, that means that the z-score of the first observation is 0.5. All right, so how do we compute the standard deviation? Very simple. We say, okay, let's take the first observation, right? Let's call it x1, right? That's the first one in our data set, minus the mean, 7. That gives you how much? 1. So let me tell you a little bit about this section, okay? One thing we're doing now is we're going to look at two variables, okay? Like age, the age of the person and the income of the person, right? And we're gonna try to get some insight as to how these two variables are related, right? As age goes up, what happens to income, right? Does it go up, down? Well, it usually goes up with age, right? At least on average, until you retire, then it really drops back down, right? So that's the point of this section, okay? To look at two variables and to compute and to use measures that will tell us something about how the variables are related. Very useful topic for, when you're running a business and you want to predict things, what's going to happen to sales. But wait, what are the things that drive sales and how it's related to sales, right? So you need to know about variable relationships, right? So it's called measures of association, all right? We're going to look at two of them. So let me tell you a little bit about the formulas, because it gets really a little overwhelming, right? We've seen so many green boxes today, and there are more to come, okay? And it's like green boxes times 2, because we get one for samples and one for populations, right? It's like variables. Should they have a positive or negative covariance? Positive. They tend to move together, right? As you get older, on average, I'm not saying that everybody does that, right? You may decide to stop working at the age of 30, right? Or whatever, okay? But as you get older, you tend to earn more money. Age is a variable, income is another variable. They move together, okay? It's hard to say as you get younger, you make less money because nobody gets younger, right? But in theory, as a variable goes down in value too, right? The other variable goes down in value as well. If they go together in the same direction, they're positively related, okay? If they go in opposite directions, they're negatively related. All right. So how does the formula work? Do you see a difference? I like actually having the formula side by side. It's much easier, right? You can just see the difference, okay? Difference, of course there's a difference. There's a difference in the notation. Instead of x bar, we have mu, right? Instead of small n for the sample, we have big N. Instead of S, sigma. Now be careful, right? This is not just S as in standard deviation. The subscript here is very important, right? What is the subscript? XY. So why would you buy the new one? You will find it in chapter 3. Okay? Covariance. The covariance, just think of the name, covariance, right? It's going to be very similar to the variance. Okay? It's going to be very similar to the variance formula. So covariance, the you can think of it coming from the word co-movement, right? The covariance measures the relationship between two variables, but it measures the linear relationship, okay? And that's a key word there, okay? Linear relationship. So when I say co-movement, I'm saying when variable x goes up, what is variable y doing? Okay? Is variable y going up? In value, I mean, right? When variable x goes up in value, what is variable y doing? Is it going up? If it is, then they're positively related. If it is going down instead, they're negatively related. So basically, if two variables move in the same direction, we say that those variables have a positive relationship. If two variables move in opposite directions, we say that those variables have a negative relationship. If two variables don't have any relationship, then we say that they have no relationship, right? So the covariance will be 0. Okay, so let's look at how that translates into the covariance. Two variables that have a positive relationship, that means that they move together, right? Are going to have a covariance that is going to be greater than 0, positive covariance. Two variables that move in opposite directions are going to have a negative value for the covariance. And two variables that have no relationship are going to have a 0 covariance. How is that? Good? So you take two variables, x and y. Now we're looking at two variables, not just x, but x and y, right? X and y, two variables. You compute the covariance. The sign of the covariance is really most of what we care about. The sign of the covariance. But we also care about the size of the number. But the sign of the covariance, whether it's positive, negative, is telling us about the relationship, whether it's positive or negative. Okay? So if you think of age and income, if you look at those two, everything repeated. Okay? So let me tell you about these 4 formulas we're going to see here. Okay? It's really 2 formulas, right? Really 2 concepts: covariance and correlation coefficient. But times 2 because we gotta look at the formula for the sample and then the formula for the population, right? Now, as far as the correlation coefficient, the formulas are different just because of notation, okay? The only difference comes from notation. So as far as computation, same thing, okay? And when it comes to covariances, the formulas are different because of notation, but also because of computation, okay? There is a slight difference between the 2 formulas in terms of how they're computed. Just like the variance formulas, right? How they were slightly different because of the n minus 1 and the big N, right? Very similar. Okay? So just so you know, this topic is not on chapter 3, it's on chapter 14. But on your homework, it's all already there, right? So you do have a homework question on this one and a quiz question on this one. All right. I should say that again. This topic here is in chapter 14 in your book. So if you don't find it in chapter 3, then you got to go to chapter 14 and find it. Okay? It doesn't make it more difficult because it's in chapter 14. In every book that I've seen, actually in the new edition of the book, they moved to chapter 3. So if you have the new edition, which I doubt you would, it's just too expensive.